this. So I'm going to walk you through the physics of it, although it's trivial. It's almost as simple as what Denny was just saying, and then you'll understand why. My partner thought at one point that you could take color and make it into depth, because light gets bent through things like prisms. So I'll explain how it works. Consider we have like 5 circles on the screen, a red one, orange, yellow, green, and blue. They would all look equidistant to your eye because they're just on the screen. Okay, let's say I have 2 wedges of plastic, acrylic, polystyrene, okay, 2 prisms. And I put one in front of my left eye, and I took the identical one, but I flipped it around in front of the right eye. Okay. Now, a red ray from the red circle would come into my left eye, and since I have the option of putting the prism any way I want, I can have it bend the ray this way. The right one, on the other hand, since I flipped the prism, will bend that ray to the left, both towards my nose. And those 2 rays, one from each eye, will intersect here, some point in space, but in front of the screen. Okay, because we bent the rays of light, and your brain doesn't know that the intersection wasn't really due to a red ray coming from that point. Similarly, orange, yellow, green, and blue would do the same thing, except it would be bent through different angles. Okay, so we have a red ray here, yellow one, orange, yellow, green, and blue. So color has been mapped into depth. As you'll appreciate later when you see the film, you lose color for its own sake. Anything which is red anywhere in the image, in any image, will be closer than yellow, green, and blue, because that's what the optics do, and they don't care. So it's not a true process the way the polarizing process of the movie, for example, or a TV process, where it's true 3D. Okay, so with 1 prism in front of each eye, we get a spread of distance from red to blue. But unfortunately, in order to get a decent separation between red objects and blue objects, we need a high dispersion prism. That means that the index of refraction, or how it bends light, is large. When that happens though, red appears very close to your face. And if you try and look at your index finger with your finger very close to your face, you'll see how painful that is. It's hard to focus on this because it's right in the picture. The muscles don't want to do that. So ideally, we'd like to have the image of red here and then blue much further behind. But we can't with a single prism. In order to get a separation, red has to be here. So my partner picked a different prism to do the second part of the job. Polystyrene. It was acrylic and polystyrene. Actually, that's not even true. Originally, he did it with liquids. He built little microscope slides, like a little rectangular cell with a diagonal. He put cinnamon oil in this half, very high dispersion liquid, very dangerous, very corrosive, but he needed it, and then glycerin on the other half. The second prism, second liquid, takes the image we created with the first prism and pulls it out into space. It increases the refractive index and pulls the image out. So now we have red at a comfortable distance and yellow, green, and blue at a nice separation. And basically that's how it works. It took 5 years to develop the film because the enabling technology did not exist in '85. In fact, we were just about to quit in '89, another 4 years into the effort, when MIT started to work with an area called binary optics. Instead of a prism, they used something else called the diffraction grating, which bends light in a similar fashion, and the problem was solved. And it shows that actually, if you're an entrepreneur and you're trying to bring an invention to market, you do need some luck, because we came this close to stopping. Okay, I won't take any questions now, but if anybody has any, please see me later, and thank you.